you can. And then I say, welcome everyone to the COMSOC video seminar. It's great to have you back. As you know, we're going to have, again, weekly meetings in the coming months, we hope. And you can find already the program for the next few sessions on the website. This includes, in particular, on the 24th of September, a so-called rump session, which means that 8 people each will give a very short talk of 5 minutes, and then we have a couple of minutes for questions for that talk. And we're still looking for a couple more volunteers for that session. So you can, if you would like to participate, you go to the website, you will find a form there, you can enter your name and we'll get in touch with you. All right. Today we have 2 speakers. I'm looking very much forward to their talks. Let me introduce the first one, and Doro, you can, while I'm doing that, you can start sharing your screen. So our first speaker today is Dorothea Baumeister from the University of Düsseldorf. Many of you will be familiar with some of her work and will know her probably. So she's worked on various topics in voting, in judgment aggregation, also argumentation related to social choice, very often with a complexity angle, but typically mixing this in also with the more economics type perspective, the axiomatic perspective. And today she's going to speak about manipulation of opinion polls. And it's a great pleasure to have you here. Please go ahead.
Yeah, thank you. Why don't I see my slides anymore?
So I can see your slides, so they are there.
We see your slides.
I don't see them. Okay, I will do it once again.
Yes. We practiced all of this before, just in case people are wondering whether we just show up here and no, we had a proper practice session, but it's still difficult.
I saw them just before, so now they are back. Okay, so thank you for giving me the opportunity to give a presentation here in this nice seminar. And I want to talk about manipulation of opinion polls to influence iterative elections. And this is joint work with my PhD student, Ann-Kathrin Selker, who cannot be here today because she's currently on maternity leave, and with Anna Wilczynski, and I think she's here today from the Technical University in Munich. This talk is mainly based on a paper from this year's AMOS conference, and since AMOS was a completely virtual conference with many recorded talks, I'm very happy to be able to present the work here today. So I would start with a short example to introduce the general setting. As for a usual election, we have a set of voters. Here they are called A, B, C, D, and each of them has a linear order over the candidates, which are represented by colored dots. And this means here in this example, A prefers red before blue, before green, and before yellow, and for the others like this. And in our setting, we additionally have a social network, and this is represented as a graph, as you can see. Here we have the social network, and there the voters may be connected. And this is, if you have an arrow from A to D, like this one, that means that voter A observes the ballot of voter D. And in addition, we have an opinion poll. This is what we have here. So in this example, we assume that we evaluate the election according to the plurality rule. And the opinion poll announces the plurality score for every candidate. And in this example, the red candidate is 2 times on the first position. So the plurality score for the red candidate is 2. The green and blue candidates have a score of 1, while the yellow candidate has no points. And the idea is now that the voters have the information from the opinion poll and then can decide to change their own vote. And these changes may be observed by other voters if they are properly connected in the social network. And the voters then combine the information from the opinion poll with the changes that they observe. And we assume that they deviate from their original vote if the information makes them think that this would change the outcome in their favor. So the main components are a set of candidates and the preferences from the voters. We consider 2 specific voting rules here, plurality and veto, and we have the social network and the public opinion poll. The motivation to study this setting is to capture, for example, political elections and dynamic tactical voting. And even if a voter has made an opinion about the candidate, her voting intention may still change until the real election. And the strategic game model is now iterative voting. And there are different sources of information. In our model, the social network may model the relatives or friends that individuals have, and they may talk about their opinion for an upcoming election, and so they gain knowledge about their ballots. And on the other hand, there's the public opinion poll, which models the public announcement before an election. And there's a lot of work studying different forms of iterative voting. And in this talk, I will focus on the manipulative role of the polling agency. And so we want to find out whether it is possible for the polling agency to influence an election in a specific way just by announcing a manipulated result as the opinion poll. And this might lead people to change their votes, which then may have an impact on the outcome of the election. So one key component in this model is the modeling of the individual views of the agents. In general, we do not assume that the social network is a complete graph, and that means that a voter does not observe every change in the votes. And this leads to different believed scores from different voters. And to formalize this, we introduced the notion of believed scores. So the real score of a candidate, in this example, I took the blue dot, is the number of points she gets under plurality or veto elections. For plurality, it is the number of first places, while for veto elections, it is the number of last places. And the winner in a plurality election is then a candidate with the maximum number of points. And in a veto election, it's a candidate with the minimum number of points. So BIT is now for the blue dot, the believed score of the blue dot for agent I at step T. And we assume that at every step, only one single voter changes her vote. So to start in the beginning, we have BI0, and this is the score of the blue dot, which is announced by the polling agency. And then we have the step from T to T+1, and here the score depends on the deviation of the agent. So here we consider the case where agent J changes her ballot. So we have to distinguish three different cases. In the first case, the believed score of the blue dot will be decreased by 1. And this is done because in the social network, there is an edge from agent I to agent J. So you see here, the edge from I to J. And agent J initially voted for blue here, but at step T+1, she deviates to a different candidate. And here in the next case, we increase the score by 1 because agent I observes that agent J, who initially voted for a different candidate, now changes her vote to a vote for blue. In all other cases, the believed score of the blue dot will remain the same, and all remaining cases are listed here. So the first one and the second one is agent J deviates to the blue candidate or it deviates from the blue candidate, but now there's no arc from agent I to agent J, so agent I does not observe this change. Or in the last case, J changes her ballot, but neither from nor to the blue dot. And in this case, it doesn't matter whether I observe the change or not. And so here the score stays the same. And since we interpret veto here as a minimization problem, the update of the believed score is identical for plurality and veto. And the changes in the vote refer to the first position for plurality and to the last position for veto election. So now we have defined the individual views of the agents at every step, but it's still missing how and when the agents actually change their vote. And here we may take a rather simple approach. So we assume that the initial state is the truthful voting profile, and the initial believed scores come from the public opinion poll. for the best response, which means the decision how and when a vote is changed, is different for both voting rules considered here. In the case of plurality, the best response of agent I at step T is to approve of a most preferred candidate, which can win with an additional vote according to the believed score BIT. And this means a voter changes her ballot only if she believes that this change will result in a better winner. In the case of veto, agent I will veto the current believed winner according to the believed scores if this would make a candidate win, again according to the believed scores that this agent prefers. So the polling agency takes a central part in our setting, and we generally assume that the opinion polls announce some global information and that the voters trust this information. And the exact information that is communicated by the polling agency is the number of points or vetoes for each candidate. And now we want to study how wrong information in such an opinion poll lead to different winners of the election. In order to keep the most basic credibility in the polling agency, we assume that the opinion poll respects a very mild likelihood condition, which says that for no voter it would be possible to see that the information is manipulated at the first step. This is, for example, the case if a voter observes 3 ballots voting for candidate blue through the social network, but the opinion poll announces only 2 votes for the blue candidate. And additionally, we assume that the sum of the points corresponds to the number of voters. And this is the only restriction that we study here for the manipulation. And one could, for example, also assume that voters have some memory where the previous information is stored, but we do not consider this here. And then we consider different kinds of manipulation. So the first distinction is between constructive and destructive manipulation. In constructive manipulation, the goal of the polling agency is to enforce the election of a distinguished candidate, while in destructive manipulation, the polling agency just wants to avoid the election of a distinguished candidate. And we study 2 different restrictions. So in the poll restricted variant, we assume that the Manhattan distance between the scores announced by the polling agency and the truthful scores is bounded. And this models the scenario where the polling agency tries to modify the scores as little as possible. In the voter restricted case, we assume a bounded swap distance between the submitted ballot and the truthful ballot. And this is, for example, important if a voter doesn't want to make too obvious changes that in turn may be observed by other agents through the social network. So here is a small example for destructive manipulation. So we have a veto election with 6 voters, and the first 3 ABC have the same preference. So they have this preference. Then we have 1 voter D and 2 voters E and F, again with the same preference. In the social network, we assume that A sees the changes from voter B and C observes the changes from D. Then we need some tie breaking in order to be able to determine unique winners, and the tie breaking that we use is just an order over the candidates. And the truthful opinion poll would announce these points here for a veto election, and that means initially every voter thinks that with 0 votes, with 0 vetoes, red would be a winner of the election. Obviously, for the first 3 voters and for the last 2 voters, that would be a very good outcome. And they don't want to deviate from the actual ballot since they are most satisfied with the outcome. For D, it's not the perfect outcome, but the best response is again to not deviate, since it's not possible to make a more preferred candidate win by giving a veto to the red dot. And that means no voter deviates here, and hence red is the winner of this election. And now we assume that there is somebody who absolutely dislikes the red candidate and tries to destructively manipulate the election through the opinion poll. And that means we ask whether there is a different possible announcement for the initial opinion poll that satisfies the likelihood condition such that a different candidate than the red one will be the winner. So in this example, it is possible. Consider this different announcement from the opinion poll, which you can see here. And now we need to have a look at the voters, whether they want to deviate or not. And in this case, the voter D deviates to a different vote because when voter D gives a veto to the red dot, which is shown here. Oh no. Here. Then that would result in a tie between the green and the red dot, both having one veto. And if we then take the tie-breaking rule, then the green candidate would win, and so D deviates to a vote, giving a veto to the red candidate. And this deviation is now observed by voter C according to the social network, and C then updates the believed score since she saw voter D changing her ballot from giving a veto to blue to giving a veto to red. And according to the tie breaking, she deviates by giving a veto to green in order to now make the red candidate win the election. And now no voter has an incentive to change her vote, so the winner can be calculated. And in total, with these two changed votes, we have 2 vetoes for yellow, 3 for green, and 1 for red. And this means that blue will win the election, which means that the destructive manipulation was successful. And as you can see, the new outcome, blue, is worse than the old outcome red for every single voter. And this implies that the destructive manipulative power of the public opinion poll is very important. And to study how hard the manipulation is, we formulated a corresponding decision problem and studied the computational complexity. And the good news is that constructive and destructive manipulation is NP hard. And this holds even if the network is acyclic for unrestricted and restricted versions. And it holds for both voting rules that we consider plurality and veto. And constructive manipulation remains NP hard under plurality, even if we consider the poll restricted version when the network is empty. But on the negative side, we have FPT algorithms with respect to the number of candidates when the network is empty. And this holds for the constructive and the destructive manipulation problem. And for unrestricted, poll restricted, and voter restricted versions, and again for plurality and veto. And we also have polynomial time algorithms when the network is empty. And for veto, this holds for all variants and versions, but for plurality only for the unrestricted and poll restricted versions of the destructive variant. So our results imply that in general, it is hard for the polling agency to manipulate. But as it does not prevent manipulation in practice, we want to design efficient heuristics to enforce or avoid the election of a specific candidate. Here we consider, again, the blue candidate. And the general idea of our heuristics is to test pairs of candidates, X and Y. And these pairs are such that X will be announced as a winner by the polling agency and Y will be a potential winner. And then for plurality, we distinguish between 2 variants. So in the constructive variant, we favor pairs XY, where Y is our blue candidate, and many of the voters prefer Y to X. And whereas for the destructive variant, we have the pairs where Y is not the blue candidate, and many voters prefer Y to X. Similarly, for veto, we have the constructive case where we have pairs XY, where X is not the blue candidate in the constructive case, and many voters prefer Y to X. And in the destructive case, we favor the pairs XY, where X is the blue candidate, and among the voters vetoing the blue candidate, many of them have to prefer Y to X. And for our experimental setup to test our heuristics, we consider different target candidates for the manipulation through the polling agency. So in the constructive case, we generally try to enforce the election of a bad candidate to make manipulation hard. And so bad candidates are, for example, the Condorcet loser, the border loser, or the truthful loser. And in the destructive case, we want to avoid the election of a very good candidate, and the counterparts are the Condorcet winner, the border winner, and the truthful winner. So the results of the experiments are shown here. We considered elections with 50 voters and 5 candidates. We took the impartial culture assumption and considered only acyclic graphs. This is important since if we don't have acyclic graphs, we cannot always guarantee that it converges to a stable outcome. And in blue are the results with no manipulation, which means that the pollen agency announced the truthful scores, and the heuristics are the results from the idea that I very briefly described on the previous slides. And exact means that all possibilities to manipulate are tried for the pollen agency. And the picture now shows the frequency of successful manipulation for the different cases, and for both plurality and for veto elections. And on the left, you have the constructive case, on the right is the destructive case. And you can see that the heuristic performs quite good when compared to the exact case, and this is especially true in the destructive variant. And in the constructive variant, the results for the heuristic are still good, but for veto, they are better than for plurality. And additionally, we made some experiments for the exact algorithm where we try every possible manipulation. And we did it in order to compare different variants of manipulation that we studied here, which means we have the constructive and destructive variant, and we have the 2 voting rules, plurality and veto. And in the experiments, we now considered 5 candidates, and the number of voters varies from 10 to 50, and the votes are still drawn according to the impartial culture assumption, and we again consider acyclic networks. And from the results, you see that the destructive variant is easier to manipulate successfully than the constructive variant. And the rules that we consider are rather symmetric, because either you give an approval for one candidate, or you have the veto against one candidate. But in terms of manipulation, this makes a difference that you can see here from the picture. Okay, so to conclude here, the main results of my talk. So both variants of manipulation through the polling agency are hard in the worst case, even for an acyclic network. But there are polynomial algorithms for some cases. For example, when the number of candidates is small, or for veto in the destructive case, when the network is empty. And additionally, there are efficient heuristics that are simple that we have seen here. And in general, manipulation is more successful under veto in the destructive variant. And to the end, I will just mention some directions for future research in this direction. So we considered only 2 very simple voting rules. So next step would be to extend it perhaps to general K-approval rules. However, it is here important to define the best response dynamics accordingly, because it's a bit more unclear if you have more candidates how best response should look like. Or in the next step, you could consider general scoring rules. And the choice that we have for the best response is a rather pessimistic one. So one could also consider more optimistic variants where deviation must not directly result in a different winner. And this is also closely connected to the next point, where voters with memory could be considered. And the last point is to provide more information for the polling agency, like, for example, a partial knowledge over the votes. Okay, so this is the end of my talk, and thank you for listening, and I'm happy to answer your questions now.
Thank you very much. May I invite everyone to unmute themselves for a round of applause. Thank you very much. So, Doro, I think it's good if you stop sharing your slides, then yes, we can all see each other a bit better. And there are already several questions in the chat. Anael was working very hard and answered many of them.
Thank you.
I think while we go to a couple of them, if other people want to type in more questions, please do. So I think there was one by Ilan has also been answered. Okay, so by Bill, that was not answered. With 50 voters, how many edges in the network? Did you compare sparse networks with rich ones?
No. The reason why we did not compare it is because if we have 2 less edges in the network, then that would make manipulation less successful because we don't observe so many vote changes, but we did not do these experiments.
Then there's one by Peter. What do you observe in the social network? The full preference order or just the candidate that somebody votes on?
Only the candidate who is voted for, so the first or the last candidate, either for plurality or veto.
And then I think, so the last one is by Piotr that I think has not been answered. You can also read it out yourself and comment.
No, we didn't look at other vote distributions. We only made these experiments for impartial culture. But it would be nice to look at other distributions as well.
And which order updates did you check?
Sorry, I couldn't understand.
Oh, sorry. And which order of the updates in the network did you check in your experiment?
In which order do they change? Is it round robin, or in which order do they update their vote?
No, there is a fixed order. I didn't mention this. There's a fixed order over, so we can assume a fixed order over the voters, and they update in this fixed order.
But can you characterize what are they? Whether there are some orders are harder than that, or to manipulate by the poll maker?
That's an interesting question. So we didn't look at this, but I'm sure there will be voters that are harder to manipulate, but we did not study this.
But your hardest proof did not give you an intuition of whether there is a specific order that gives you this hardness.
I don't think that it gives the right intuition. No.
Okay, thanks.
I'm not sure whether any of the people who got a very quick answer from Anael, or maybe I just overlooked it. So if there's a question already in the chat by somebody and that they feel it has not been answered adequately, please speak up. Or if you have a new question, please ask. Yes, Alan.
A question. So you mentioned homophily in your experiments. Did you find that, like, what behavior did you find in terms of homophilic graphs versus other graphs? Did you find any particular trends?
So we didn't study different types of graphs in our experiments. So that would be something to look at in the future.
So I have a question about this believed score. So you have a certain belief about what the scores are, and then you, so do you somehow, are there any effects that you, because what you remember from what the believed score was in the past, that you can make conclusions about how it should be now? Or is it always enough to just look at the last state?
No, so if you consider more advanced agents, they should remember what happened in the past, but from now we did not consider this. So we assume that the voters only know the actual state and they forgot what happened in the past.
Okay.
Is the poll being repeated, or is there just a single poll and then all the updates have to be done locally by what you observe in the network?
So in this setting, we really consider that there's only one initial poll and we don't repeat the poll, but there are other settings where it is considered that the poll will be repeated and updated.
There's a new question in the chat, /idea by Piotr.
So I did not consider this. I think this is more an idea that we can think about, but I have no answer to this to the question from Piotr.
Then I think Alan is a suggestion or a call to arms, maybe. Yeah.
I think in terms of experiments, there's a lot of room for testing different things and a lot of room for having final results.
Okay, are there any final questions? I want to wait a few seconds, or you can just unmute yourself if you want to ask. If not, thank you very much once more, Doro. It was a very nice talk. Let me explain for those of you who are new to this, what's going to happen next. So this is the coffee break. So Dominic is going to randomly allocate you to a breakout room where I think around 10 people will be invited to join each of these breakout rooms. So you can say, you can accept or not. Please feel welcome to say yes. And then you're going to go into a separate room with a smaller set of people and you can have a chat while you're having your coffee, which I hope you have at hand. And after 10 minutes, we're going to call you back. So you will see a message there blinking and then you click on it and then you come, or even if you don't click on it, you just come back. And, but you can also take a proper break and not see any of us for 10 minutes. And we're going to start again 10 minutes from now. So see you then. All right, wait a few more seconds, just in case people are still coming back. Okay, I think we can get started. Sid, you can already start sharing your screen. Then it's my great pleasure to introduce our second speaker, Siddarth Barman from the Indian Institute of Science at Bangalore. Sid is working, is a theoretical computer scientist working on a number of things, including things in algorithmic game theory, for example, equilibrium computation, and in computational social choice, for example, kind of fair division work that we're going to hear about today. It's a great pleasure to have you here, and I'm looking forward to your talk.
Okay, so let me start by thanking the organizers for this invitation. And yeah, this is a great, so seminar series is a great initiative, and it's a pleasure for me to be sort of participating in it. So today I'll talk about a recent joint work with Nidhi Rathi, and the result sort of develops algorithms for the classic cake cutting problem. So the story of algorithmic game theory has been a story of impressive bad news. I mean, many of the central solution concepts that are supported by very strong existential results turn out to be computationally intractable. And this sort of saga repeats itself in the fair division literature, where on the one hand, we have like very strong existential results that say meaningfully fair allocations of resources exist in sort of fairly general settings. But on the other hand, we don't have algorithmic counterparts. Like, while these fair divisions exist, it's not obvious, and in some cases there are impossibility results that rule out efficient algorithms, polynomial time algorithms, to find those fair divisions. And what we do in this work is sort of circumvent those barriers, circumvent them by looking at sort of a specific family of instances. And so at a high level, what we do and what I'll talk about today is to sort of identify a rich class of instances and show that for them, we can in fact develop efficient algorithms for in this classic cake division model. And the talk will be sort of almost self-contained, but for those of you who know what cake division and cake cutting is, let me just sort of foreshadow the key insight, which is that for this class of, for a specific class of instances, what we do is we develop an alternative proof of existence. And the insight here is that many a times novel proofs of existence go hand in hand with new algorithms. So this sort of complementary relation also holds in the sort of setting we consider. And in particular, and again, this is for people who are sort of somewhat familiar with cake division, which I think is a large fraction of the audience here, is that instead of using the heavy hammer of fixed point theorems in general, or Sperner's lemma in general, what we do is that we show that for a specific class of instances, for an interesting class of instances, we can just use the intermediate value theorem to prove existence of fair cake division. And recall that intermediate value theorem is nothing but fixed point theorem in one dimension. So with this specific an instantiation, we sort of get the result, and then sort of we'll see how we are able to easily constructivize it to get the algorithm. So here's the context, here's the general setup we'll be talking about. We're going to focus on the division of a divisible heterogeneous resource. So the resource is divisible in the sense that it makes sense to talk about fractionally assigning it to the participating agent. So it makes sense to say that 1/3 of the resource is given to the first agent, 2/3 of it is given to the second agent. At the same time, the resource we are going to sort of try to model is going to be heterogeneous in the sense that different parts of the resource are valued differently by the agents involved. And formally, this resource is modeled as the unit interval 0, 1, and it's referred to as a cake. So this model captures division of applications such as division of land, spectrum allocation, or even scheduling, time scheduling on a machine. So again, given the audience and in the interest of time, I'll not belabor the rich history of this problem, multiple textbooks written on it, or the applications of it. Rather, I'll just directly jump into the model at hand. So as I said, the cake is modeled as the unit interval. Divisibility is captured by the fact that I can assign subintervals, so pieces of cake, so to say, among the agents. And heterogeneous aspect of this model is captured by the fact that different agents have different valuations. So the cardinal preferences of the agents in this model, in this setup we are considering, are represented or expressed by these valuation functions, wherein for each agent A, VA denotes the value it has for different intervals. So throughout the talk, the subscript is going to identify the agent involved. So A is the agent here, VA is its valuation function. And again, we'll conform to this very classic setup that the valuations are induced by density function. So agent A has a density function over the unit interval, over the cake, and you can think of it as a measure over the cake. And the valuations are obtained simply by integrating with respect to this density function. That is, I'll just look at the area under the curve for an interval with respect to A's density function, and that will tell me how much A values this interval I. So if I look at some other interval J, again, I just integrate with respect to A's density function, look at the area under the curve with respect to A's density function, and that will tell me the value A has for this other interval J. The talk is not going to be notationally heavy. So pretty much the only sort of construct that I'll carry along will be this valuation function. So now what are we looking for? What is the desiderata here? The idea is to partition the cake into n connected intervals. So I want to make n minus 1 cuts on my cake, on my unit interval. And then the n subintervals that emerge, I want to assign them among the agents such that fairness is achieved. Now, do note that again, the subscript here denotes the agent involved. So in this figure, for example, IEA, the leftmost interval is assigned to agent A, the next interval IV is assigned to interval B, so on and so forth. And every agent with its density function evaluates the value it has for the interval assigned to it and to the interval assigned to the other agents. And the quintessential notion of fairness in this context, the gold standard in cake cutting and more broadly in fair division literature, is the notion of NB freeness. So I'll say that a division of the cake, so a partition of the cake into n pairwise disjoint connected subintervals, is fair if it is NB free, by which I mean that every agent values the interval assigned to it at least as much as it values any other interval. So in this inequality, do note that I'm evaluating both the left-hand side and the right-hand side with respect to agent A's valuation. So A looks at the interval assigned to it, that is IA, and then says that I value it at least as much as I value IB for any other agent B. So there are n choose two such inequalities, and if they hold for a partition of the cake into these intervals, then I'll say that that's a fair division. That's an NV-free division. At this point, and if you haven't seen this before, it's certainly not obvious that such a thing can exist, let alone such a thing existing in sort of any level of generality. But the very sort of somewhat surprising and sort of classic result of Stromquist, and the very beautiful proof by Su, shows that under very mild conditions, such a division actually exists. And so in particular, if you have valuations that are continuous, then there necessarily will exist a partition of the cake into n intervals such that NV freeness is achieved, i.e. these inequalities hold for every pair of agents. But as I said before, the party gets cut short, because while I have this very strong existential result, at the same time I have a fairly strong negative result, again by Stromquist, who showed that in fact there is no finite time algorithm to find such an NV-free division. So this negative result holds in an adversarial model. Nonetheless, it kind of says that you can't hope to have, let alone a finite time algorithm in vast levels of generality that will find for you and NV-free division, which by the previous result is actually out there. So with this backdrop of a strong negative result, let me state our contribution again. What we show is that for an interesting class of instances, we can in fact find NV-free divisions efficiently. We can find them in polynomial time. There's some technical aspects of arbitrary precision, so on and so forth. But for the purposes of talk, I'll ignore it. If you want to go into these details, I'll be happy to talk about it offline. But for the time being, when I say NV-free, I pretty much mean NV-free. There's a small additive error. I'll sort of, again, for the short talk, I'll ignore that detail. And so what do I mean by broad class of instances? Well, the property, the capturing property, the encapsulating property we look at is what is called the monotone likelihood ratios property. It's a property that applies to the density function of the agents. I'll define it in a few slides, but let me just mention that there are like a number of well-known distribution families for which this property holds. So in particular, if the densities of all your agents are Gaussian, then our result holds, that is this monotone likelihood ratio property holds, and our result will apply. If on the other hand, the value densities are linear, again, the property holds, our result applies, and you can find NV-free division. In fact, any linear translation of a log concave density would satisfy this monotone likelihood ratios property, and hence our result sort of in a single sweep captures a lot of well-known distribution families. So let me start by defining this property for two densities, F1 and F2, Fi and Fj, and then I'll generalize it to n densities, F1 to Fn. So as the name suggests, what the property says is that if I look at two densities, Fi and Fj, then their likelihood ratio, which is Fj by Fi, is non-decreasing over the cake. It's kind of easy to see this property for this picture, in particular for F1 and F2. At the left end of the cake, the ratio, the likelihood ratio F2 by F1 is less than 1 because F1 is more than F2. When the two densities intersect, the likelihood ratio becomes equal to 1 because F2 by F is equal to F1, so F2 by F1 is equal to 1. And as I go to the right end of the cake, that is I go to 0.1, then F2 is more than F1, so the likelihood ratio in fact becomes greater than 1. So for F1 and F2, you can see that the likelihood ratio F2 by F1 is increasing as I move from the left end of the cake to the right end of the cake. And similarly, you can check it for like say F2 and Fn, so on and so forth. And extending this idea, we'll define that a collection of densities satisfy this monotone likelihood ratio property if the consecutive likelihood ratios are increasing. So I look at the likelihood ratio of agent I plus 1, the density of agent I plus 1, the density and the density of agent I, and that likelihood ratio, if that's increasing for every I between 1 and n minus 1, I'll say that this collection of densities satisfy MLRP. It satisfies the monotone likelihood ratio property. So do note that the definition is sensitive to an indexing. So what I'm saying is that agents are indexed such that the consecutive likelihood ratios bear this MLRP property. So that's a technical definition. The intuition here is that compared to agent I plus 1 is putting more mass to the right of the cake. So there's a question, let me just answer it. So yeah, so it's not symmetric in agents. The definition holds for a particular ordering among the agents. So for a cake division instance, like we can say that the cake division instance satisfies MLRP if there exists some ordering over the agents such that this happens. So yeah, I'm just, again, for ease of notation, I'm just going to assume that upfront the agents are indexed such that the monotone likelihood ratios are sort of increasing for every consecutive pair of agents. And the intuition, as I said, is that compared to agent I plus 1 is putting more mass to the right of the cake. And in fact, this intuition is sort of substantiated by a characterization which we show in our paper. And this is a characterization, so it's an if and only if condition. And if you don't want to think about densities, the characterization only refers to the valuation. So recall that I integrate the densities to get the valuation. And what this characterization says is that not only do I have stochastic dominance among the agents, I actually have stochastic dominance for every interval. So what do I mean? I mean that let's take any two intervals L and R, the left interval and the right interval. And now if I look at two agents I and I plus 1, and if I normalize their valuation by the total value they have for the entire interval L union R. So I'm looking at the denominators here. So VI L union R and VI plus 1 L union R are the normalizing factors. What this says is that for any pair of left and right intervals, I plus 1 values are under this normalization more than I. So this is an if and only if condition. If this ratio, this stochastic dominance like property holds for every agent I and I plus 1 and for every left and right interval, then I'll have if and only if I have MLRP. And again, do note that this characterization also is sensitive to like a specific ordering among the agents, and it's also transitive. So while I've stated it only for I and I plus 1, the while I've defined it only for I and I plus 1, the property actually sort of holds for any I and J where J is more than I. So there's a question by Rohit saying that, is it well defined for say negative valuations? No, like, so in particular, do note that if I'm looking at the likelihood ratio, I do want full support. So that's one sort of implicit constraint that's been imposed by the definition. FIs have to be non-zero throughout the cake. And the next question is, would it suffice to assume that only finitely many subintervals? Yeah, so it has to be the right set of subintervals. Yeah, I mean, I don't think a priori you can like assume that this is going to be going to hold in general. So let me now, given that I have like 5 or more minutes left, let me just finish the talk and then I'll address the remaining questions. So this is the characterization I have. It's sort of a stochastic dominance per interval kind of a property. What I want you to do is sort of instantiate it for a specific value of L and R. What that will let me do is actually segue into the sort of key construct, the key sort of intellectual idea of the result, the sort of notion that we define. And with that, I'll be able to sort of tie everything together. So let me actually instantiate this characterization for a specific LNR such that agent I is indifferent between the two intervals. So what I'm looking at are intervals L and R such that VI of L is equal to VI of R. And the observation, the somewhat simple observation I'm going to make is that if I then assign the left interval to I and the right interval to I plus 1, agent I plus 1, then there will be no NV between them. So obviously I is indifferent between L and R, so I will not NV I plus 1. But at the same time, a simple calculation shows that, in fact, I plus 1 will also not NV I in this setting. Why is that? Well, look at the ratio on the left-hand side. The denominator splits up as a sum because L and R are disjoint. The values for L and R are the same for I. So the ratio on the left-hand side is exactly equal to half. Then the inequality is exactly just rewriting the characterization, again, splitting the denominator as a sum. And then if you solve for it, what you'll get is that I plus 1 values R at least as much as it values L. So this allocation is going to give you like a no NV solution, at least between I and I plus 1. Okay, so let's make a mental note of this property. And the reason is that with this, I'll segue into the key notion that we define, sort of the light bulb of the talk. And what I'll show to you is that this new notion actually is going to give us NV freeness overall when I have this MLRP, when the densities satisfy the monotone likelihood ratios property. So what is a ripple division? So here's the definition. We'll say that a set of points starting from 0 to 1 constitute a ripple division. So these are points x0 starting from 0 and xn at 1. If the ith interval and the I plus 1th interval from the left are of equal value to agent I. So it's a mouthful, so let me actually parse it step by step. So what the definition is saying is that if I look at the leftmost interval and the second interval from the left, so that is 0, x1 and x1 and x2, then these two intervals are of equal value with respect to V1, with respect to agent's 1 valuation. Then if I look at the second and the third interval from the left, then those two are of equal value with respect to the second agent's valuation. So why am I forcing this inequality? Okay, you should see some connection to the observation I made on the previous slide. So, and so on and so forth. And then the definition dictates that the ith interval, which is between xi minus 1 and xi, and the I plus 1th interval are of equal value with respect to agent I's valuation with respect to Vi. So with this in mind, let me actually index and assign the interval. So I'll give the leftmost interval to agent 1. So label it as I1, give the second interval from the left to agent 2, so on and so forth. So with this assignment and the definition of ripple division, what I have is that the valuations with respect to agent 1, she's indifferent between the two leftmost intervals. Agent 2 is indifferent between the intervals she has been assigned and agent 3's interval, so on and so forth, till agent I get to agent I, and she's indifferent between the interval that's been assigned to her and the next agent I plus 1. So very quickly in 2 minutes, I'll actually show to you that with this definition, I get MLRP. And the idea again is to just invoke that observation. So let's fix agent I plus 1. And so I'm going to prove NV freeness with respect to I plus 1. So I look at the intervals I sub I and I sub I plus 1 and let them be the left and right interval. The fact that they are of equal value with respect to I means that, again, directly instantiating the observation I had made before, that I plus 1 actually values her interval, which is to the right, more than she values I sub I, which is to the left. I can actually now chain this idea. Now, again, I look at intervals I sub I minus 1 and I sub I. So these are my left and right intervals. And now, again, I'm looking at agent I plus 1, not agent I. And then these two intervals, so the left one being I sub I minus 1 and the right one being I sub I, are of equal value for agent I minus 1. So these two are of equal value. Again, what I have is that agent I plus 1 actually values the right interval, which in this case is I sub I, more than the left interval, which in this instantiation is I sub I minus 1. So this is somewhat quick, but you can see that I just reapply that observation over and over again to get this chain of inequalities, which says that if I look at agent I plus 1, she actually values the interval assigned to her more than any interval on the left. And in fact, as you move to the left, the valuations keep on decreasing. Things are completely symmetric here. So what you get is, in fact, NV freeness for all agents. So what I've done so far is like defined a new notion and showed you that under MLRP it's NV free. But how do I know that such a thing even exists? And I'll stop my talk by proving that such divisions always exist. I can prove that, and in fact find a ripple division and hence find an NV free allocation. So the key idea is to actually justify the adjective ripple, justify the name. And here the simple observation is that once I fix the first cut point, once I fix x1, all the subsequent cut points are like completely determined. So with x1 in hand, I can use v1 to find x2 by looking at this equality. Once I have x1 and x2, I can use v2 to find x3 again by looking at this second equality, so on and so forth. So all I'm saying, there's some technical conditions here of Lipschitzness and so on. But what I'm saying is that once I fix the first cut point, say x1 prime, which might be different than x1, the last cut point is fixed. Like it's just a ripple through these equalities. So if you pick an x1 prime, this is very close to 0, you might follow these equalities and actually not assign the whole cake. On the other hand, you can start off with a very high x1 prime and like run out of the cake. But in all cases, what I'm saying is that the last cut point here is just a composition of these inequalities. It's a continuous function of the first cut point. It's a one-dimensional function. It's just maps one point between 0, 1 to another point between 0, 1. And hence, using the intermediate value theorem, I can actually guarantee that there always exists a starting cut point, a golden x1, such that the last cut point through these equalities actually falls at 1. So in particular, what intermediate value theorem gives me, i.e. fixed point theorem in a single dimension gives me, is that a ripple division always exists, which I've already shown to you is under MLRP is NV free. So for this MLRP, for this very broad class of instances, I have existence of an NV freeness through the intermediate value theorem. And since I can constructivize the intermediate value theorem, which is simply like binary searching for the right x1, I can actually constructivize the whole idea. The arbitrary precision issue comes here, like binary precision does leave the eta gap. Nonetheless, that's a technicality I'm skipping for now. But nonetheless, the yada yada yada, what I have is that via binary search, I can find the x1, the golden x1, and hence find a ripple division. The implication in the box above tells me that ripple division is guaranteed to be MLRP, and hence the result we have is that when I have MLRP, there's a polytime, a binary search based algorithm that gives me an NV free cake division. So I'm out of time, so I'll just flash the additional results I have, some of the open questions that I find interesting, and let me stop here and address any more questions that you might have. Great, thanks.
Thank you very much. Let's unmute ourselves and for a round of applause. Thank you, very interesting. So I think there are still a couple of questions in the chat that haven't been answered yet, so maybe you can go to those first.
Yeah, so Rohit asking like for MLRP for, yeah, so it does lead to other, yeah, so I just kind of flashed it towards the end, yeah, so you can use it to find, for example, egalitarian optimal solutions, and again, up to arbitrary precision, now social welfare, up to arbitrary precision, and polytime. Equitability too. I think equitability you can actually do slightly more generally. So yeah, it does lead to sort of other fairness and efficiency measures. interestingly, every NV-free allocation in this, when you have MLRP, then every NV-free allocation is guaranteed to be Pareto efficient. So it's not just that there is some NV-free allocation that's economically efficient. Everyone ends up being Pareto efficient. So sort of a very, it's a gift that keeps on giving in that sense, MLRP. So the other one was that, yeah, what about indivisible items? Yeah, so I do think that's sort of an open question. And yeah, I do think that characterization that I mentioned, like looking at unions of sets and then applying that should help even in the indivisible case. In particular, like looking at sort of discrete goods on a line and trying to, so that's been like a model that has been studied recently. So I do think in that case, MLRP should give us some positive results. Yeah, so Edith has, in what scenarios do you expect to see such densities? So, yeah, so I didn't go too much into it, but for example, if all the densities say are Gaussian with different means for the same variance, then MLRP holds. So that kind of captures a setting where there's a single peak preference. So every agent has a most preferred point on the K, and her density sort of decreases as a Gaussian as you move away. So in that case, that's sort of a natural setting where you can, like where MLRP holds and the results would apply. Yeah. So that's one one setting. I'm sure like yeah, it's quite broad. So exponential log concave densities and so on. So they do show up in many settings like binomial polynomials. So all of this are captured, encapsulated by this nice property, and so they will continue to hold. Can you modify a ripple division to generate the set of all possible EF participants into with respect to initially? Yeah, I mean, I don't think so. Like I mean, I do think there are examples where there are NV-free divisions that are not ripple divisions, even with MLRP. So here's like a simple case. So consider a setting where all the agents have the same value density. So there's no monotonicity, there's no unimodal, like there could be multimodal, so on. It's just that all the densities are the same. So the likelihood ratio, it's a trivial case. Nonetheless, the likelihood ratio is 1 all the time. So in those cases, you can't, like there's no fixed order there's no single order that satisfies MLRP. So you can have different orders and hence different NV-free allocations. And even more generally, I do think I'd be surprised if it's the case that ripple divisions capture all NV-free divisions in this MLRP context. They should be like, it's just a nice subset of NV-free divisions. The next one says, if the order of the agents is unknown. Yeah, sure. I kind of, so the question was, what if you don't know the MLRP order? You can. I mean, it's quite easy. It's just the fact that you'll have stochastic dominance. So we kind of detail a simple algorithm to do it. If I give you an instance with the promise that there is a hidden order that satisfies MLRP, you will be able to figure it out efficiently. So that's, yeah. So I completely stated it as a centralized. So the question is like, your algorithm is centralized. Can it be expressed in the Robertson web query model? Yeah, everything everything works in the Robertson web query model. It's just for the purposes of the talk that I kind of said it as such. The binary search is the algorithmic part, and that you can execute using cut and eval queries. So it's pretty much, so modulo the MLRP assumption, nothing here is beyond textbook. Like this is works in a standard query model for cake divisions. If more than one of the agents share the same density curve and evaluation, can there be NV-free division? Yes, I mean, let's say I just have all the agents have the same density, then you partition the cake into pieces of value 1 over n for this everyone, and then you will have NV freeness. So certainly, yeah, you don't, I mean, the results hold quite generally, even if the density curves are, all actually you need is the Lebesgue integrability of the density curves, nothing more. So, which would imply the continuity of VA, and you'll have NV free division. So existence is like hauntingly generous, hauntingly general.
Did you answer the question by Edith about in what scenarios do you expect to see such densities that?
So that was the Gaussian like example. Yeah. Okay. So like yeah, the single peak preference with Gaussian fall. So that would be like one case. So there have been some empirical work that look at like random like points and the densities dropping off as a Gaussian as a noise model. But yeah, so in that sense, like that's one case where the results would apply. Yeah, it kind of highlights the fact that like in this like prior work had looked at some of the more like, natural classes like piecewise constant and so on, and those aren't really captured here. So it does say that for if you're looking for algorithmic avenues in this sort of these kind of context, you might want to look at other encompassing properties than the ones that are inspired more by like the discrete world or the combinatorial world.
Okay. Are there any questions that haven't been answered? Then please speak up now.
Which concept of computability on reals do you use here? None. So we just work with a finite bit precision model, and that's the point I kind of alluded to, that you will have a arbitrary small loss or an arbitrary small error term in your final solution. So the NV will be additively eta close or eta small, and that's it. And I mean, and that's sort of unavoidable because I can give you instances with rational input that the unique NV free solution is at irrational points. So you sort of address that like by looking at sort of this precision by saying that like formally the result says that you can find an NV free division up to an arbitrary precision in polynomial time. So
maybe Bill's first question about if MLRP is satisfied on finitely many subintervals. Would that transfer? It was the beginning of the discussion.
Yeah. In general, I'd be surprised if that's the case. I would want to, yeah. I mean, if it just so happens if it satisfies for the right, I mean, at the end, I just need it for the cut I find. It's like a chicken and an egg kind of. So at the end, to prove NV freeness, I just need it to hold for the ripple division or for a ripple division. So in that sense, yes, like if it just so happens that there is a ripple division, and if you just instance like the x1, x2s that I was referring to, if it holds for that, then you will have NV freeness. So in that sense, yes, but yeah, I mean, a priori, I don't know what those are. So it sort of goes back and forth in that sense. Does that make sense?
I think it will have to make sense because we would like to finish now. This was a great discussion. It's wonderful that people have so many questions. Thank you very much once more. So that concludes today's seminar. Let me announce what we're going to do next week. We're going to meet on Thursday at the time at which we met today. We're going to have Hans Peters and Marcos Privato speaking. It should be great. I'm looking forward to it and hope to see many of you there. We still have 2 open slots for the rump session in 3 weeks' time, more or less. So if you feel a little bit shy about speaking yourself, ask one of your students to fill in the form. See all of you, I hope, next week. Bye-bye.
Bye-bye.
Bye.